All right. Greetings, YouTube. Beautiful mind here. This aka Professor C. All right. So this is going to serve as a lecture for our calculus for business. We're moving into chapter 2. So chapter 2, we're going to be talking about exponential and log functions, right? So with chapter 1, we explored some concepts behind derivative. We looked at the limit of the difference quotient definition of the derivative. Then we saw some rules and some shortcuts for finding a derivative. Okay, so we're going to move into chapter 2 with this exponential and log functions. So with section 2.1, we want to explore exponential and log functions of natural base e. So some objectives here: we want to graph and solve exponential functions of the natural base e, and then we want to graph and solve log functions of the natural base e. Okay. So we have this definition. The natural base denoted e is the value given by the limit as n goes to infinity of 1 plus 1 over n to the power of n. Okay. So as n goes off to infinity, this expression approaches this number 2.7182881 blah 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 blah, right? So like that's the limit definition of the number e. So e is like, it's just like a function, kind of like pi, where pi is like 3.14. Sorry, it's like really early. I just woke up. So e, this is the limit definition of e. Okay. So theorem 1, we have this continuous exponential growth. A quantity p growing continuously at an annual percentage rate r expressed as a decimal has a future value after t years given by this. So from college, this is a continuous compound interest from college algebra. All right. So when something, or you could say, you know, it's a continuous compound interest from college algebra, right? Where p is going to be the starting amount of the principal, r is the annual rate of growth, and t is the time in years. And this will tell us how much of that item is there if it grows continuously throughout the year. Okay. So continuous growth. Lewis invests $5,000 in an account that earns interest at an annual rate of 3.25%. Find the future value of Lewis's account after 5 years if interest is compounded continuously. Okay. So again, continuous compound interest. I call it PERT, P-E to the RT. Okay. The future value. Okay. So then the future value is going to be the principal. So he starts with $5,000 times e to the power of the rate. So if we have 3.25%, we have to write that as a decimal. So the percent symbol, you can look at it meaning as a per 100. So if we divide by 100, that's going to become 0.0325. So the rate has to be expressed as a decimal, and then we want to let it sit for 5 years. Okay. Oh, I'm trying to. Okay. Then you would just use your calculator there. Let me pull up my calculator. Okay. So then we're just going to do 5,000 e if I hit second, and then ln for natural log. There's the exponential function, 0.0325 times 5. And so after 5 years with those conditions, it's earned $800. So $5,882.24. Okay. All right. I'll put this over here. Okay, and then you see a typed version of what we just did. Okay, on to the next one. So, oh shoot, oh, that's a quick check. Okay, I'm gonna leave this one as an exercise. This should kind of be a repeat. You see everything worked out there. So you're welcome to walk through this one. I'm gonna leave this one as an exercise for you. So then we have a definition for any positive number x. The natural log or logarithm base e of x is going to be given by the natural log of x is the common log of x base e. All right. So again, ln is going to be common log base e. If you don't define the base for common log, then in general the base is base 10. All right. But here we're saying that the natural log is common log base e. The equation y equals natural log of x is equivalent to, so if we were to write this log expression, if we were to write, let's do this. So if y equals the natural log of x, then that's going to be the same as y equals the log of log base e of x, right? And then if, I gotta go, I'll fix that later. So then if we were to write this in exponential form, we can swing the base over here. So then this is going to be the same as e to the power of y equals x. And you should see it. It should be the same here. All right. So I think from college algebra, we can write logs in exponential form, and we can write exponentials in log form, right? If we just swing the base back and forth and with a certain technique, these are equivalent. So y equals the natural log of x is the same as e to the power of y equals x. Okay, so they're like inverses of each other. Well, these are equivalent, but we can use, logs and exponentials are inverse of each other. So find each of the following. If necessary, use a calculator. Okay, so for the first one, the natural log of e, they essentially cancel each other out and the exponent comes down, so this one should just be 4. Okay. Natural log of 1, that's just going to be 0. You can even, if you didn't know that natural log of 1 is 0, you can actually use your calculator and you should see that one. The first two you can use your calculator and get those, it'll spit out those results. Again, natural log and e are inverses of each other, so they cancel. What's left is the exponent there. So that one should be -1. And the natural log of 20, I would just say use your calculator. I'm going to say calculator. Okay. So it should be 4, 0. Okay, so they rewrote the logs as exponentials. That's fine. So remember, natural log of e to the 4 is the same as log base e of e to the 4. If we wrote this in exponential form, that base e is going to swing. So then we'll have e to the y equals e to the 4. And this is only going to be true if y equals 4, right? Right there. Again, this is going to be the same as e to the y equals 1, right? And that's only true if y is 0. This one's going to be e to the y equals e to the -1. This is only going to be true if y equals -1. And then using a calculator, you get that one. Okay. I like the way they did it. I know the way they did was a lot more concrete. So yeah, they use the technique of rewriting the logs as exponentials and then solving the resulting exponential equation, or they just use the calculator. So we have some properties of natural logs. The log of the product is, the log of the product is the sum of the logs. The log of the quotient is the difference of the logs. The log of the power is the power times the log. The log of e is 1. Okay. Properties 1, 2, and 3 require that m and n are positive. because the domain for log is strictly positive. Okay. Okay. So then the log of 1 is 0. Let me see. Okay, so this is the change of base with property 6. The log of m base b is the same as natural log of m divided by natural log of b. That's change of base. And the natural log of m is also going to, remember, this is going to be log base e. Let me see. Give me a moment. I feel like something is missing there. This one looks like it might be a typo. Because this one is fine. Log of m divided by, or the natural log of m divided by natural log of b. But it seems like this is missing something here. Like I feel like either this should be e or something, but I feel like there should be something a little bit augmented there. But we'll catch those. We'll catch those as they arise. I can't think of like what's missing here, but we'll catch them as they come. Let's see. The natural log of e is x. So remember the natural log and e are inverses. They cancel, and the power goes in front, and this is the result. Same thing here. E of the log, again, these guys cancel, and the x persists. Okay, I'm gonna let that be for now. Given natural log of 2 is this, natural log of 3 is this, use the properties to find the following. Natural log of 6, right? So natural log of 6 is the same as the natural log of 2 times 3. So then that's going to be the same as the natural log of 2 plus the natural log of 3. So then that's going to be this 6931 plus 1.0986. And then that's going to be, basically we're adding those two together. I gotta use my calculator. Just trying to be a little bit quick and cognizant of time. So we just add those two pieces that were given to us. 0.6931, that's not a 1, plus 1.0986. 7917. Okay, I'm just gonna go with that. Natural log of 81. 81 is what, 9 times 9, so that's 3 to the power of 4. So natural log of 81 is the same as natural log of 3 to the power of 4. That's going to be the same as 4 times the natural log of 3. And that's going to be 4 times this 1.0986. So then we're going to say 4 times 1.0986. 3944. Okay. Natural log of 1/3 is going to be the same as the natural log of 1 minus the natural log of 3. Natural log of 1 is 0, so then that's going to be negative. Natural log of 3 is 1.0986. Okay. So the log of the product is the sum of the logs, so this is going to be the same as the log of 2 plus, I'm going to go ahead and bring the power down. It's going to be 5. Actually, it's just going to be 5. It's going to be 5 times the natural log of e, but then they cancel, right? So then it just leaves the 5 there. And natural log of 2, so it's going to be 5 plus, ultimately we're going to get 5.6931. Okay. So we can use change of base here. This is going to be the same as natural log of 3 over natural log of 2. That's going to be 1.0986 divided by 0.6931, right? 0.986 divided by 6931. Okay. So then we get 5851 approximately. We had around 5851. Okay. Let's see, the first one 7917, the second one 3944. We got this negative 1.5. I think these are all good. Yeah, okay. All right. So we have this next theorem. Let me see my time. Okay. Natural log of x exists only for positive numbers x. The domain is this. Oh, so natural log of x. So the domain of log is positive, strictly positive. The graph, there's a vertical asymptote on the y-axis, and then you have a, really, really close to the right side of 0. It's nearly a vertical line, and then it kind of like curves off to the right. That's the graph of natural log. So it's only defined for positive number x. Natural log of x is negative when x is between 0 and 1, is 0 when x is 1, and positive when x is strictly greater than 1. This function is always increasing and the range is all reals. Okay. Find the domain. Okay, so again, in general, log function, the domain is going to be strictly greater than 0. So this guy here, this 5 minus 2x has to be strictly greater than 0. If we solve for x, 2x, divide both sides by what? 2. In this case, x has to be strictly less than 5 halves. So in interval notation, the far left is going to be, x is going to go from negative infinity up until 5 halves. Infinity always gets parentheses, and 5 halves in this case gets parentheses because we don't actually include 5 halves. So for this example, x is going to be defined as long as x is strictly less than 5 halves. Okay. You see a type version of what we did. Okay. Find the domain. Same thing, right? In general, that the inside part has to be strictly greater than 0. So this 7 minus 3x has to be strictly greater than 0. If we solve, 7 is strictly greater than 3x. Divide both sides by 3, 7/3. So then the far left would be negative infinity up until 7/3. Infinity always gets parentheses, and this gets parentheses in this case. Okay, you see it here. Okay, where x is solved here, give answers to 3 decimal places. So for A, so let me see, will that help us? Yeah. We can take the natural log on both sides. On the left, we're going to be left with 3x. On the right, we're going to be left with natural log of 2. So then x is going to be equal to the natural log of 2 divided by 3. And so that's going to be approximately. So if we do natural log of 2 divided by 3, it says 3 decimal places, so 0.231. Okay, and then for B, Okay. So first I would divide both sides by 250, and we would get e to the power of 0.015t. That's going to be equal to, what is that, 3? We divide both sides by 250, we should get 3 on the other side. Then it's a repeat of the previous. Take the natural log on both sides. So natural log of this, natural log of this. These two are going to cancel. On the left, we're going to be left with 0.015t. On the right, we're going to have the natural log of 3. So then t, divide both sides by that 0.015. Natural log of 3 divided by 0.015. And so t is going to be approximately 73.241. And then, with these we can plug these results back into the original and confirm that they work. And because because we rounded these, or these approximations, it should be really, really close to the, it's not going to be exact, because the rounding is going to throw things off. We got 231 and 241. So you see the 231 here, and then, okay, I put 241, they put 24, but it's the same thing. Okay. All right. Let's see what time. Okay, I think we're doing good. So it says the exponential growth rate r expresses the decimal, and the doubling time are related. Let's see. So the doubling time, they call it a t, capital T. Exponential growth rate. Okay, I'm just gonna let those be. I usually think of it a little bit different, but yeah, it's fine. I'll let it be for now. Okay, so Facebook connects people with other members they designate as friends. During this period, the heaviest growth membership in Facebook was doubling every 6 months. What was the exponential growth rate of Facebook membership as a percentage? Okay, before I look at it, I'm going to do it the way, like, the first one, the way it first appears in my mind, right? So I'm going to use it. I'm going to eventually get to the point where the previous slide was at, but I kind of want to start here. Let me see. I said a PERT. I kind of want to say like A of T, A naught E to the, I'm going to say RT, right? This is like exponential growth. Let me see. It was doubling every 6 months. Okay. So whatever we start with, we're going to finish with twice that amount, twice the starting amount, right? E to the R. What was the growth rate is what we're trying to find, and 6 months. So that's going to, 6 months is half a year. So that needs to be in years, right? So then we can divide both sides by the A naught. A naught is like the starting amount or our principal. So they essentially cancel in this case. We'll switch to black. So then we're going to have 2 equals e to the 0.5r. Then if we take the natural log on both sides, we're going to have the natural log of 2 equals 0.5r. So then the rate of growth is going to be the natural log of 2, or you can say the natural log of 4. There's a couple of ways you can look at that. I guess a simple thing, let's just go ahead and divide by 0.2. I mean by 0.5. Dividing by a half is the same as multiplying by 2. Let me just take it a little step further. This is going to be the same as, so dividing by 0.5 is the same as dividing by 1/2 If we divide by a fraction, we do keep, change, flip. So that's going to be the same as 2 times the natural log of 2. Ultimately, that's going to be the same as the natural log of 4. Let me see. I'm going to see something on the previous right here. So the doubling time, so r is going to be the natural log of 2 divided by the time. Remember, our time in this example is 6 months, half a year. So that's where the 0.5 is, okay? And you see how we have the 0.5, the natural log of 2 equals 0.5 times r? You can see it here. Instead, that's why I didn't say anything here. I didn't want to just like remotely say, okay, this is the doubling time. I wanted to do it from the exponential growth formula. So you saw how we started with the exponential growth formula. And then, so what we started with some amount, and then we doubled it. And then it said it doubled in half a year, right? And I just wanted you to see where this came from instead of blindly just accepting it. Okay. So then natural log of 4. It should be okay. We got approximately, what is that, 39? 1 point. Let me think about this. 39%? Or is it 100? There might be, let's see how they get, what kind of answer we get. Oh, looks like we are off. We have 6 months. Why did they do it in months? Oh, they did it per month. The mine is per year. Okay. So let's convert. This is per year. So let's convert this to months, right? This is per year. Okay. Let me do this conversion. So if we have 1.39, let's see. So per year, then let's see if we say times 1 year is what, 12 months. So we're putting it back into months. So then let's take our answer and divide by 12, and it should match theirs. Yeah, okay. So then we get this 11.55% per month. Okay. Okay. So yeah, because I had converted mine to years, and I was like, well, usually, yeah, we do these in years, but they decided to do it in months here. Yeah. Yeah, that's fine. So the growth rate, it grew by 11.6% per month. Okay. Yeah, they left it in terms of months. Okay, I'm gonna let that be. So let me see the time. We're asked to solve. Okay, let's solve this. Let me start by getting a copy of the original. We have this 5 plus 7 times the natural log of x plus 3 equals 19. So we could subtract 5 on both sides. We'll get 7 natural log of x plus 3. What is that, 14? Divide both sides by 7. Natural log of x plus 3 equals 2. To bring it out of the log, we can raise both sides to the power of e. On the left, we're going to have x plus 3. On the right, we're going to have e to the power of 2. Subtract 3, e squared minus 3. Then we're going to say x is approximately. Okay. I'm going to do 4.389. Okay. And you see a typed version of all what we just did there. trying to wrap this up because I'm seeing my time. I'm trying to still adhere to the 35 minutes. Oh, and the section summary. There you go. Okay. All right. So yeah, that's essentially the items that I wanted to say there. I just wanted to kind of work through those examples. Ooh. Okay. So yeah, I can't think of anything else I want to say there. We're gonna hop off and hop back on and go ahead and do the next section as well. And on that note, we're going to end the session here. And from one beautiful mind to another, see you in a few minutes.